Uber is a transportation company with a high volume of temporal spatial data, constantly being collected from the devices of its users. At any given time, the engineers and data scientists at Uber need to be able to query the system and understand what is going on with drivers and riders. The unique real time engineering requirements of Uber lead to an interesting architecture. Danny Yuan joins us today to discuss Uber's data engineering and how the company makes use of its streaming data. If you're a fan of Software Engineering Daily, we'd love it if you would fill out our listener survey. Check out our newsletter or on our website. You can click on the survey and fill in the information about how you consume our podcast. We really want to know how to serve you better, what we can add to the podcast, and what we should subtract from it. Thanks for listening to Software Engineering Daily, and after a quick word from our sponsor, we will get to this episode of Software Engineering Daily. The nature of money is changing, and software engineers are the creators of that change. On Software Engineering Daily, we've done shows about Bitcoin, automated trading, Ripple, and other financial technologies. One thing is clear: there has never been a more innovative time in financial technology. Untapped has jobs at the world's leading fintech companies. Untapped is a platform for matching software engineers with jobs at fintech companies. Sign up at untapt.com/sedaily and find a job in fintech. If you're invited to interview, Untapped will send you a collection of 5 books relevant to both your interview and this week's episodes on Software Engineering Daily. These are books like Cracking the Coding Interview, or Manning books, or O'Reilly books, and they're really going to help you get the knowledge that you need to get the job that you want or create the piece of technology that you want to see brought into the world. There's more at untapt.com/sedaily. That's untapped.com/sedaily. Untap your talent today at untapped.com/sedaily. Now let's get back to this episode of Software Engineering Daily. Danny Yuan is an engineer at Uber who works on stream processing architecture. Danny Yuan, welcome to Software Engineering Daily.
Thanks, Jeff. Thanks for having me.
Uber is an enormous transportation network, and at any given time, the engineers and the data scientists at Uber need to be able to query the system and understand what is going on. What are the application requirements for this kind of system?
Okay, well, I can't speak for all the use cases or all the users, but at least for the stream processing marketplace, which is mainly the team that I work for, here are a few requirements. First one, we need to process multiple event streams. Like many companies, Uber has multiple distributed applications working together, and different applications generate their own events. And sometimes we need to put different streams together to extract useful information. And the second is those events should be available within seconds, and they should rarely get lost. A little bit of loss occasionally might be okay because largely we're generating aggregations or analytic data. And about data itself, so each data usually has dozens of different dimensions or fields and many different metrics. And almost all the events has geospatial information such as latitude and longitude coordinates, and we need to process them. And also there are quite a number of common operations we need to perform, such as sessionization, aggregation over geo areas, or joining multiple streams. And some of the processings may require multiple steps as well. And also, we need to support good queries and pattern discoveries. So for queries, we mean like ad hoc queries. Our users should be able to slice and dice our data in any combination of dimensions on the fly, and they should be able to filter data by arbitrary Boolean filters. And also, we must be able to organize geo areas as different grids that may sometimes tens of thousands of cells per city. A grid can consist of S2 cells, user-defined geofences, or statically mapped hexagons. As for pattern discovery, there are rich patterns in event streams, and we wish to identify them in real time. For example, we like to be notified if more than 20% of riders in the area couldn't get any cars 5 times in a row. Yeah.
So let's start at the event creation point, which is you have drivers and riders all throughout the system, and constantly there are events coming off of their phones, geospatial data, and those events hit Uber, and you guys ingest that data in a way, and then you collate it with other data, and you want to format it in a way that can easily be queried. So give me an idea of the types of data that you are ingesting and how you transform that data to a data store that is more easily queryable by these types of internal systems that you need to build.
Okay. Oh, well, so most of the data, we track all kinds of crucial status. Like a driver makes a call, makes a request. Oh, sorry, a rider makes a request to a driver in order to get a car. A driver picks up a rider. A driver drops off a rider, so on and so forth. So all kinds of critical events and status transitions or all kinds of state changes will be recorded. And when we get this data, first of all, we remove all the personal identifiable information because we don't really care about them. We care about the marketplace as a whole, right? And we don't want to leak those informations. And then we identify all kinds of useful dimensions, like where this thing happens, at what time this thing happens, and also like the type of the vehicle and the nature of the status change, so on and so forth. And then we just index those data in a particular storage.
Give me an idea of how you do that indexing.
Indexing? It depends on the use cases. For the real-time use cases, we index them in Elasticsearch for now.
Okay, and why do you use Elasticsearch?
Use Elasticsearch? Well, we use Elasticsearch because it fits our use cases, right? So we need to look at our use cases again. We need to perform this so-called ad hoc queries that we don't really know what kind of patterns will exist before user actually runs them. For example, users want to find out how many open cars are in a particular area in a city. Right. Then those filters by city, by geo area, or the group by different geo areas will be up to the users. And also, we don't really know what kind of dimensions we have. Different events may have different dimensions. So in this case, we really need a system that can support aggregations and also support multiple indices without us manually managing them. And Elasticsearch happens to have all these kind of features built in.
You have talked about the problems with key value stores. Why can't you store this data in a key value store?
We could. It's just, I don't think it's efficient enough. So key value stores by nature associates a piece of data by keys, right? So it's a single key. But the queries, as I described, is really so-called online analytic data. It's OLAP, right? Online analytic platform. Yeah, processing. So it's an analytical queries. The queries that you need to generate all kinds of combinations for particular data and return those data sets as a whole. So if you use key value pairs, either you have to make thousands and thousands of calls to each individual key, or you have to build like really convoluted or involved caching. Either way, it's not efficient enough.
To start to get a better idea of your stream processing architecture, how do you use Apache Kafka?
Kafka is really our data pipeline. So we use that in two different places. One is when we get data from Kafka directly, right? Because Kafka is connected to all kinds of applications inside Uber, and Kafka is really efficient and has high throughput. And the other one is we use Samza, and Samza is a processor built on top of Kafka. So Kafka is like the backbone or the internal data pipeline for Samza.
Okay, so to clarify, do you use Kafka as like the event ingestion layer, like kind of as a buffer for all the events that come in? Okay. So you also use Kafka in place of Hdfs, and we've done a number of shows on big data architectures, and I find this pretty interesting. So why is Kafka a sufficient replacement for how many people use Hdfs?
Oh, Well, I wouldn't say we replace HDFS with Kafka. It's really in the architecture of SAMSA itself. If you look at SAMSA, and it has a bunch of workers, or in SAMSA's terms, containers. And then the containers are managed by Yarn, which is part of the Hadoop system ecosystem. And now the only difference is the data that comes out of a container or goes into a container, and that kind of process doesn't go through HDFS because HDFS is not that efficient for this kind of for the streaming processing scenarios. We just need one direction of data flow, and we need to make sure this one direction is fast enough, has high throughput, and also is durable. And Kafka happens to be this kind of system. It supports high throughput and traffic. It's very efficient. It has a very simple distributed model, and also it's durable, right? So it's elastic. It's a queue, and then the different processors can process data in their own pace, and they don't worry about losing data or they don't worry about being left behind. If one process slows down, then later it can pick up where it's left off. And so Kafka fits this use case, and actually it fits very well.
We recently did a show about Alluxio, which is trying to provide a layer of faster access just slightly higher up the stack than HDFS. Alluxio used to be called Tachyon. Have you looked at Alluxio?
Yes, a little bit. So we look into that for our processing layer built on top of Spark. And we want to have a smarter and out of heap caching layer, right, to make our Spark jobs run faster. And Alluxio is the number one candidate.
Interesting. So I would like to get a better idea for how you use Elasticsearch. So your Elasticsearch is divided into warm and cold storage versions. Can you explain the motivation for this?
Well, the motivation is we have different query patterns. And we also deal with data in different ways. So if you look at our data, when the data is first ingested into the system, then we call it real-time data or warm data, right? Because at this time, if someone wants to query this data, they probably want to have this data available almost immediately, as fast as possible. But also in the meantime, they don't have to look back for a very long time. They probably want to ask questions like, "Hey, what's going on right now?" or "What has been happening in the past 5 minutes?" So in that case, latency really matters. Then we have this warm layer, then we have SSD as our permanent storage, and we have ample memory for those machines so that we can hold as much data as possible in memory. And usually in-memory data runs faster. But then if you look at the historic data, then sometimes people really perform queries that spans across hours or sometimes weeks. So in that case, we want to have larger storage, cheaper storage, so we can store more data. But in the meantime, we can wait longer. Then we call it cold storage. And on the other hand, it's also about isolation of concerns. For historic data, it's usually used by data scientists or engineers for investigation purposes. If it goes down for a minute or two, that's okay. Right, we can bring it up gradually. We don't have that much of pressure. But for real-time data, usually it's used by machines, and machines needs to make decisions that serve customers. So we want to make sure this cluster is well isolated. It will not be impacted by historic data, and it's always available.
Great. So Uber uses a Lambda architecture, which is a term that is overloaded and used in a lot of different ways. How do you define the Lambda architecture?
My definition is pretty similar to what everyone else is thinking. So we have a streaming processing layer that processes data on the fly, which may have some problem, or not problems, but let's say the data may not be always complete, or we may have to take some like approximate route. And then we have a batch processing layer that implement almost identical logic. And this batch processing layer will be used for backfilling the data or maybe used for repairing the data as needed.
Okay. And so to give a better idea of the different ways that you use stream processing frameworks, or I guess I should say just processing frameworks, you have Apache Spark in your architecture, and as you mentioned, you have SAMSA also. So people who may not maybe they've been listening to the show or they've been reading about these different processing frameworks and they hear Spark, Storm, Samza, Flink, they hear all these different things. It would be useful if you described how you use Spark and how that contrasts with how you use Samza.
Okay. Samza is strictly a stream processing layer. If you look at Samza's APIs, it's very simple. It's called process, and then it takes an enveloped piece of data, one data at a time. And of course, you have some window functions, you have checkpointing, you have state management, but essentially, you process message one at a time, right? And then you process them, you emit your process result back into Kafka or some endpoints, and then another layer picks it up. So data flows from one direction, from one place to another place in one direction. On the other hand, when we use Spark, we strictly use that as a batch processing layer. We may download data from either S3 or Hdfs, and then we may perform like iterative processes. For example, we may piece together multiple streams from multiple locations, and we may calculate some sessions, or we may smooth the data. And all those kind of processing, the logic is similar to stream processing, but we don't but those jobs do not deal with streaming data at all.
Okay, great. So I want to go through some high-level use cases and dive down into how your architecture suits those different use cases. So first, I'd like to discuss like if I'm an engineer at Uber and I'm building like a dashboard app, then that wants to look at the ingested data from drivers and riders, and I want to have some kind of real-time picture of the health of the system and how drivers and riders are interacting, how the city is working at a given time, the Uber's infrastructure on the system. What do I need to build? How am I interfacing with the APIs that are available to me as a data scientist at Uber, and how are my queries getting processed by the system?
Okay, for dashboard, we do provide a query layer, and we don't expose any like Elasticsearch or storage backend at all. The query layer is totally abstracted out. It's like a select statement. You select from a table, you do some aggregation, and then you apply a where clause, you apply a group by clause, you apply having or sort clause, and the only extension is you may perform a do. It's like a UDF function to the data that you queried with, right? And then we have this query layer. We don't have a query language yet, which we just built, but we haven't deployed that. But we have a abstract syntax tree that represents this query language. And we also have Python APIs, JavaScript APIs, and Java APIs. And users just deal with either the AST as an HTTP payload or post payload, or they can just use APIs to access them. And what they get back is very specific set of data. We call it citywide geospatial temporal data. That's our abstraction. What you get back is a list of data that's either grouped by time, so it's bucketed by time, or it's grouped by cells in a geo area, and each cell has one or more time series data.
Okay, so a next example of something that you might want to calculate at Uber would be like dynamic pricing. Like, let's say you want to know at any given instance how aggressively people are ordering Ubers, and if there's too much load on the system, maybe you want to do some surge pricing. How does a system like that get built on Uber's streaming architecture?
I cannot talk about how pricing architecture works.
Well, certainly not the economics, but maybe the architecture of it.
Even the architecture I can talk about. I can talk about how the streaming part supports it.
Sure, perfect.
The answer is simple. By the way, there's a lot more components, services, and data sources, right? Streaming data is just one piece of the puzzle. But in this piece of puzzle, it's through the same API. So we have this query API, and this query API allows us to query what's happening right now or what has happened in the past few minutes or a few hours. And then our system can use this data to make smart decisions.
Okay. In your talk at QCon, you mentioned something called a monoidal query. What is a monoidal query?
Okay. It's not monoidal query per se. It's the data is monoidal, right? Well, by that monoidal, I mean the data supports certain operations, and those operations have certain characteristics. In particular, the data is associative. The operation is associative, and there's a identity element in the data set. And also, I was talking about so-called commutative and monoidal data, which means the operation is also commutative. The reason I mentioned that is because sometimes the data volume is huge or the processing takes a long time, so I want to parallelize it and we want to distribute it out into multiple machines. If an operation is both associative and commutative, then I can just slice and dice the data into arbitrary chunks and dispatch them to multiple processing nodes, and then perform a simple scatter and gather. And also I can form a processing tree as we implemented. Multiple machines, each machine is like a node in the tree, and that node will be responsible for fanning out the task into multiple machines again, and then return the results recursively back to the root node. In that case, we can speed up our processing. So it's an optimization technique, but it requires collaboration with the data.
So I'd love to talk some about general architectural principles of building a streaming architecture. So from the customer's point of view, and I'm certain from internally, Uber is rapidly changing. The application platform is expanding. There are different requirements for things like food delivery and carpooling. How do you architect the streaming platform in a way that is general enough to allow for quicker iteration and change and new applications?
I would say the most important thing is about the proper abstraction. So our abstraction, or the abstraction we provided, is called multidimensional geospatial temporal data. So a multidimensional means each piece of data may have different fields or different values as tags associated with it. And it's geospatial, well, because each piece of data has some geospatial information. And it's temporal because we always deal with time series data. Right, then once we have this abstraction, then our architecture is built around processing this kind of data. We don't really care about individual values or individual business cases. Another example is we need to know the state transitions, right? So in the end, it's a state transition diagram that changes over time. Then we process edges, and the edge is really just a technical term in a graph, and it has nothing to do with the name of the nodes or the metrics or the weight associated with each edges. Then each system, then each system, each applications will generate edges, or they will generate this dimensional geospatial temporal data, and then we just process as a uniform structure. So individual values do not matter that much, and we make sure that users can query such data in a very flexible way, so that we don't really have any preset assumptions. I think this is the way how we evolve. Then, carpooling has their own states. Well, it's a state transition diagram. Food delivery, they have their own state transitions. Well, it's another state transition diagram, but structurally speaking, they're just state transition diagram, and we support it.
In your talk at QCon, you mentioned that the streaming platform had to be built very quickly. Were there any sacrifices that you had to make in order to build it quickly?
I wouldn't say sacrifices, but maybe trade-offs for sure. So when we have very short time to deliver something, then we have to make trade-offs. And we focused on delivering functionalities. And the trade-off is we do automations as needed. And another one is we may be able to build something much more robust or much more flexible, but we prefer to use something off the shelf or something that our team has been operating, because that will save time. For example, for quite some time, we just used the command line tools to submit our SAMS jobs until we integrated it into our deployment and management tool. But for a while, it was actually time-consuming or tedious to submit SAMS jobs or manage them or get logs. And this situation gets improved over time. It was not built in the first phase. And also, we chose Lambda architecture instead of a more generic Kappa architecture because it was easier to implement the former. Right? So those are the trade-offs we made. And also we use Elasticsearch. Elasticsearch is great for our use cases for sure. But maybe there's some other options. Like LinkedIn has Peanut, Druid is great, and maybe there's some other things, or maybe some in-house ones. But we've really got a large install base for Elasticsearch, and we're kind of familiar with Elasticsearch. Then we decided to go to that path. But of course, we build abstraction layers on top of it. So if we have to migrate in the future, we can.
So one thing that's interesting about covering this space is that there are so many new technologies. There's things like Flink come out, Alluxio. When these new technologies come out and they seem exciting, how do you trade off between the idea when something new comes out, it seems shiny and interesting, and maybe you see the upside of it. How do you trade that off between the idea that you want to wait for something to be proven, and you also don't want to interrupt the run the business type of software maintenance with bringing in something new? How do you think about the new technologies that are constantly coming up in this space?
Yeah, tell me about it. Right? Every time we discuss about choice of technologies, there's always new one coming out, and I don't even know about it. I would say, in general, I'd be aggressive in vision, but conservative in operations. By aggressive in vision, I mean we have to constantly looking out the new technologies and see what their selling points are, what kind of things that we really look into, and what kind of things we really, really need. For example, if we look at Flink promises that they don't need micro batches. Their event processing is almost instantaneous, and they promise that they don't users do not need so many tuning knobs because they have top-notch optimizers. And they also say that, hey, you can unify your processing of streams and processing of batch data, and there's built-in iterative processing and supported. So all those things are great, and probably we will have this kind of use cases or needs in the near future. So we need to look into that. Then we try that on our laptops, and then we try that on our staging servers. But in the meantime, I'm also aware that our business evolves fast. It's not like we have a steady. It's not like always have a steady use case. And if we spend a lot of time building the next generation technologies, then we don't have time to build features, right? And also, our team is small. Like the data pipeline team started with 2 people and grew to like 4 or 5 people. Then in that case, we have to make sure the operation is as easy as possible and as transparent as possible. There's not so many hidden variables, and ideally we should be able to use those systems as a black box and only jump into code when absolutely necessary. Right, so it's really just a balance of these two. So usually, and also we look at existing system and see if we can build, if the primitives are good enough. Like for example, if I use right now, there's like Google Dataflow. Right? Google Dataflow is open source, and there's a new project spinning up called Apache Sim, and a lot of the primitives, especially the triggers and this kind of processing and responses and different promises and watermarks, they're all great. But do we jump to that thing? Well, maybe we don't have to do now because we look at the primitives provided by either Spark Streaming or Samza, and then look at our use cases. Looks like we can build something to support those ideal situations. And also we can build a layer on top of all those great systems to isolate the backend, to make the backend as transparent as possible. Then we can operate a known system for now, even though maybe not that ideal or maybe less convenient. And then we can gradually swap into better systems in the future.
So I did a show with Matt Ranney, who I think is the chief architect of Uber. And I'm thinking back to that conversation now and thinking about how the larger system at Uber is architected. How do you interact with other teams at Uber? And how do you engineer features that involve other teams?
So there are two sides. One is our which systems or which teams we depend on. The other one is what kind of teams we can serve. All right, so let's talk about them respectively. So for dependencies, we try to depend on other teams as much as possible on the condition that we can innovate fast. Right, for example, we are not building our own stream processing layer. We depend on our great data engineering team. They're running and systems, they give us really, really good support. Samza is their offering. We take them, we use them, and we give them feedbacks. And also Spark cluster, we want to use our data engineering Spark cluster. We don't want to build a new one. We do have a smaller one for experiments though. Right, because the Spark cluster running on Yarn is not supporting PySpark, for example, and then we do want to experiment with PySpark. So this is the innovation part. And we always reach out first to different teams to ask, hey, do you have this? Do you have that? And can we work together? And I believe that a platform needs to be as uniform. By the way, my own opinion, right, that doesn't reflect companies. I don't know, because it might be different. So we want to increase the collaborations, and I believe that a platform needs to have as many use cases or as many requirements as possible, so the platform can evolve into something more general or more robust, and it will save a lot of resources for the company. So that's the dependency part. That's how we work with other teams. On the other side, for other teams to offer our services, we try to make our services self-serving. Like for example, if we provide this query layer, we also want to provide a data discovery layer. So they don't have to come to us, ask, hey, what data is available? What can I do with this data? They should be able to go to a web page. They see a list of available data sources on a high level, not Kafka topics, not database tables, but data sources that describes high-level business purposes, demand, supply, user status change, things like that. And then they know which fields are available, what kind of operations are available. And then they know where the query is. They issue a query, they get a result back. Right. So, and then also the query does not make so many assumptions. That's why I was kind of insisting that this query has to be generic or ad hoc. You perform arbitrary Boolean queries. You can perform group bys, and then you can put any data in there. Once you put in there, then it's really up to the user to decide how to use that.
In that answer, you mentioned the idea of a data engineering team, and this is something that has cropped up, I think, in the past 4 or 5 years, maybe. What are the responsibilities of a data engineering team?
They provide all the data infrastructures and services that Uber needs. Our data lakes, it's also a pretty, the term has been used by so many people, but data lake means all kinds of data stores and associated services, right? Like Hdfs and the data warehouse, so on and so forth. And it also provides processing layers, right? Like Spark clusters, the stream processing clusters, and also metadata stores and this kind of things, and also data analytics.
Do members of the data engineering team, do they work with data scientists to build things for the data scientists, or do they just present things like APIs that the data scientists can use?
I think they work with them, but I'm not in that team, so I can't really speak for them.
Sure. Okay. So, one thing that I find interesting that Matt Ranney mentioned was that Uber, recently scaled from like 200 engineers to, I don't know how many you guys have now, like probably 2,000 or something in a very short period of time. And some of these new engineers have to learn how the platform works, so the stream processing platform or whatever other aspects of the infrastructure. What are the big difficulties that new engineers have in onboarding with the architecture?
It's really about, I think it's the same as in any other companies. Like each company has their own infrastructures, their own abstractions, and their own APIs, and those things work together. Right? Then for a newcomer, the newcomer needs to know a lot of things before and he or she can start. Especially she or he has to know those things conceptually. when running into some problems, then he needs to find out how to solve those problems. So that's the difficulty. It's really to know the entire environment of Uber.
Do you have any interesting experiences or maybe quotes from that rapid scaling process? Because I can imagine that this would be so challenging if you have to balance all these new employees, and you don't want a team to end up with too many employees that don't have much experience with the system. Like, maybe you could give me some insight on the management, interesting management things that have come up during your experience at Uber.
We have trainings, right? And there's engineering trainings in the very beginning, and it lasts. I think when I joined, it was a few days. Now it's almost a week. So and there's also optional courses, so people will know the general architecture of Uber, the different components, and also all the commonly shared facilities. How do you do logging? How do you how do you find and record your metrics? Where do you find all the metrics or telemetrics? And how do you work with Kafka? How do you work with our data warehouse systems? There's all kinds of courses to cover that. And in general, we have a central repository called ngdoc, and every team has their docs in there, and they have the similar formats, similar link structures, so you can find the information you need. And in general, I think people are really, really helpful. So and then we have chat rooms, we have mailing lists, and so you can just ask questions.
Awesome. So you spoke at QCon recently. I saw you there, and you also led the entire QCon track about stream processing. What did you learn from that experience?
I learned a lot. I think it's hard to say specifically. I learned how different companies perform their stream processing system, how they structure them, and what kind of use cases they have, and what kind of difficulties they have. And I'm amazed at how much, for example, in a Facebook scale, how much data they have to process, and then how they have to evolve a new system just to process to deal with their situation at their scale.
Can you contrast the challenges of Uber with the challenges of Facebook on a data scale and on the types of reliability, and how do these requirements contrast, and how do the stream processing systems reflect those requirements?
Yeah, specifically they have they require exactly once processing. I think that's really hard to achieve, right? Especially in a stream world, then the data is unbounded. There's no ending, there's no start point. So this exact once has to be windowed. And especially when the data volume is huge, how do you know that it's exactly once? How do you know it's not losing any messages? And Facebook actually solved that problem by using their pipeline. But in our case, we know this is a hard requirement. We're still working on that. And right now we settle down on a weaker requirements for at least for my team's use cases. So we can lose data, but then we cannot lose too much data. It has to be a very, very small percentage of data, and then we need to know what this percentage is.
Give us a finer idea of why that exactly once processing is so important.
In their case, they probably the use cases that they mentioned is about processing or estimating. Let me recall. I forgot which one. It has to do with money and also click-through rate or their ad estimations. So I think when money matters, then you don't want to lose important information.
Okay. Do you think that batch is a subset of streaming?
In a lot of cases, yes. If you look at our use cases, right, especially the so in marketplace, our data, the data we process, always has timestamp, right? Then if you look at streaming, it's a series of data more or less ordered by time, but there's no start and there's no end. And then if you look at batch data, it's still a series of data more or less ordered by time, but then there is a boundary. There's start time and end time. And then between this range, there's the data. So if you can process data in a stream fashion, you should be able to process data in a batch fashion. That's why a uniform model will help a lot.
What do you mean? What do you mean by uniform model?
I can just write one, let's say I write my processing logic as if I'm processing stream data. Then if it's batch data, then if I can replay that somehow efficiently, right? As if it's a stream, it's just the stream will end sometime. Then I can use the same logic to process it. It's just stream, the stream with the start time and end time.
So, to begin to wrap up, why are there so many stream processing frameworks today? I mean, you mentioned why you use Samza, but there's also plenty of other ones. How Give us some perspective to wrap up on why there are so many stream processing frameworks.
I think it's just it's the same as any technologies. People have different opinions. They have different priorities, and they want to solve different technical challenges. So over time, different system just emerges. As for example, a few years ago, there was no standard stream processing system. So Storm came out. It solves a particular set of problems. But after a while, people may ask, hey, what if I want to manage my states easily? What if I want to do this fault tolerance in a simpler manner? What if I want to do checkpointing easily? And what if I want to support durable messages without programmers worrying that too much? And what if the system can be built in a simpler way? And that came out Samza. That's my guess, of course, because I didn't invent Samza. And maybe later someone said, wait a minute, I have the batch data, and your API looks really great, but I want to use the same API and same execution engine to process streaming data. Can I do that? And Spark guy said, of course you can. Let's invent dstream and microbatches, and then you get a new system. So I think this is really that people are creative by nature, and they want to create new systems to deal with different scenarios. And eventually, multiple systems just emerge or evolved out of this kind of requirements.
Do you think there will be some degree of convergence? I mean, obviously we've kind of converged on Kafka as being the de facto choice for its use cases, but with streaming, there seems to still be a lot of churn. Do you think there will be some convergence?
I think so. There might be different execution platforms, but at least on the APIs or conceptual level, then there can be converging trends. Like Google Dataflow is a good example. The Google Dataflow provides a set of APIs that looks like very easy to use. And also Cloudera, or I forgot it's Hortonworks or Cloudera, they provide a runner on Spark. And then this Flink guys also provides a runner on Flink. And all of a sudden we have the same Apache SIEM or Google Dataflow APIs, yet they're running on different runners. And also, if you look at the APIs of Spark 2.0, or you look at the feature set of Samza 1.0, or the next, is it 1.0? Yeah, I think so. Their APIs are getting more and more similar, and they are having more and more overlapping feature sets.
Could you close by talking about an interesting engineering challenge that you're working on right now, or perhaps a feature that you're working on the stream processing framework?
I can talk about the one that I talked about in QCon, which we are still working. It's a computing platform. So the idea is, well, I wouldn't say it's a computing platform. So it's like an algorithm platform. We look at our data. Our data is largely similar. We can provide an abstraction, as I said, right? The abstraction is citywide geospatial temporal data. And sometimes we need to provide really timely processing on them. Maybe we need to transform some metrics or some time series in each cell, but at the same time we need to look at all its neighbors. And this kind of algorithms can have multiple variations or even different algorithms. And we might want to compose different algorithms together. So previously, the engineers need to know a lot about how to do optimization, how to do distribution, how to deal with all kinds of schedulings or like executors. But in reality, they don't have to. if you model this data right, it's just a stream of, not necessarily a stream of data. They can be a stream of data, or they can be a grid of data. Then each one can write their algorithms in a very specific way without worrying about how the optimization is done. And then this computing engine will take care of distribution, parallelization, data processing or data transformation, and also composition. So we provide a nice query language. Then users can say, hey, here's my step 1, step 2, and step 3. And each one will use algorithm version 1, algorithm 2 of version 2, so on and so forth, and now compose. And then magically, they just get a new algorithm out. And this algorithm can finish within a millisecond.
Okay, well, Danny, that's a great place to close. I really want to thank you for making time to come on the show. I know you're super busy, so thank you for coming on to Software Engineering Daily.
Thank you, Jeff. It's great
thanks.
talking to you.